class 2. So we're going to talk about UV vis. And so we'll start with a short introduction. So for certain topics, like why do we do slides? Why do we do handwritten? Because for certain concepts, it's better to learn it if you write it. So I really encourage you all to write everything I write. Whereas for other topics, it's less important. Okay, let's get started. So UV vis is concerned with electronic transitions. So that means that's transitions of electrons in between molecular orbitals. Big enough now? Yeah, okay. So we're going to talk about molecular orbitals a bit later, and the range is usually 200 to 900 nanometers, okay, wavelength. And it can be used to, anyone has an idea? What do you do with UV vis? It's a cool machine. You put samples, you press a button, and then. So sometimes you use it to identify molecules. So you have an unknown molecule and you take a spectrum and you say, oh, it's this molecule. Okay, there are databases to do that. Sorry, I just have to check 1 second. One thing. God. This two-screen thing is just. Where's my. Sorry for this. Just need to check. Oh. Nearly impossible. Okay, we're good. Just want to make sure I catch the sound. Okay, there we go. So you can identify molecules and you can learn about the energy levels. It's energy levels. So I said in the previous class, like spectroscopy is kind of applied quantum physics or quantum chemistry, because you can actually see the energetic levels in the molecules. You can follow chemical reactions. So I write reaction like this, reaction. It's kind of the English short notation. So RXN means reaction. And this is maybe not so relevant for you now, but later you can follow self-assembly of molecules. So molecules behave differently when they are, freely dissolved in solution versus when they are in larger structures. Okay, so what happens? So after a photon is absorbed, that goes in 10 to the minus 15 seconds, so very, very fast. The energy increases instantly, right? Very fast, comma, resulting in the excited state. And I'm going to write that M star. So that's like molecule excited. So in an equation, it would be like molecule plus H nu. right? That's the photon, gives the excited state. Okay, so once excited, the molecule is unstable and can, okay, what can the molecule do? We already looked at a couple of possibilities, right? One is it returns to the ground state by releasing heat to its environment. So that would be M star goes to M plus heat. So the ground state is état fondamental, I guess, in French. Okay, I'll write it later. Two, it can return to the ground state while emitting a photon. So that's called fluorescence or phosphorescence, okay? Phosphorescence. So M star goes to M plus H nu accent. So this H nu accent, because it's not the same photon that you use to excite. Now that photon will have less energy, will have a longer wavelength than the photon you use to excite the molecule. That's why I have this one, you know, with an accent. Here it is. Okay. Or once it's excited, the molecule can, you can use it to use the energy to start a chemical reaction that you call photochemistry. Right, so for example, M star plus X gives some kind of product. Can be different products. Or you can have an acceptor, as it's called, A, and then you can do an energy transfer. So you can, for example, get a charge on your molecule or on the acceptor, and that can have consequences for the reactivity. Okay. So the ground state or the état fondamental is the lowest energy state of the molecule. Okay. So, oh, sorry. Did I just tell? Okay, I was a bit too fast. Okay, so what is a typical experiment? You take a cuvette. Cuvette is usually made of quartz, you know, something that is optically nice. And you will put all kind of colors of light. Okay, maybe some blue. I mean, typically you put white light, right? So white light has all these different colors. And then what happens? Your molecule has a certain absorption. And you have a little detector here that looks at the light that passes through the cuvette. So the transmitted light, right? So this light would be called incident, and the light that comes out is transmitted. And the rest is absorbed, right? So the spectrum will look typically something like this, right? You have the absorbance versus the wavelength. And you will get something, whatever. We'll see what that becomes. Okay? And so the top of this peak is the most probable, oh, sorry, that's a difficult word, probable transition. And this wavelength, we call it lambda max. It's the maximum absorbance, right? It's the highest point here. Okay. So let's say that in words a little bit. So by passing continuous radiation, radiation in this case is light, through a transparent material or a solution, right? Usually solution. A portion of light is absorbed. Okay. The most probable transition is, what's the most probable transition optically in a molecule? Anyone has an idea? No? Okay, we'll get to that. Is from the HOMO, which is the highest occupied molecular orbital, right? Highest occupied molecular orbital, to the LUMO. That's the lowest occupied molecular, sorry, unoccupied, almost wrong. Unoccupied, it's a bit too fast, molecular orbital. And typically this has an energy of 125 to 650 kilojoule per mole. Okay. Okay, so if we sort the energies from the lowest to the highest energy, molecular orbitals, we find first sigma orbitals. So they come from sigma bonds, right? Then we have pi orbitals, N, so non-bonding orbitals. And then we have anti-bonding orbitals. So that could be pi star and sigma star. Okay. I guess you are here somewhere. Okay, so let's draw some energy levels. Okay. Okay. Yeah, this you cannot do on paper. That's too bad, huh? Okay, so up. That would be the energy. And so I would have from the bottom, the lowest sigma orbital, pi, non-bonding, pi star, anti-bonding, sigma star. Okay. And so initially, those levels are, these ones are unoccupied. And these ones are occupied. So which one is the HOMO? It's this one, right? HOMO will be this one. And the lowest unoccupied will be this one, LUMO. And then we can have all kind of transitions, right? Sorry, I should put this a little bit on the side. Okay, so the most probable transition we just said is the one from the HOMO to the LUMO, right? So this would be an N pi star transition. And this one is a little bit higher energy. This would be the N to sigma star. This is pi star. And this would be the most energetic transition, would be sigma pi star. Okay. So one thing to keep in mind is that we said in the previous class, to get absorption, you need a photon of the right energy. So the photon needs to have the same energy as the transition, and it has to be allowed. So some of the transitions are forbidden. So what is that, right? So forbidden transitions. So there are many type of rules and things, and they're all very approximate, and we're not going to go into that in a lot of detail. But they often involve a spin flip during the transition. Okay, so they change. You know what this I dot E is? It's like a it est. It's like Latin for that is. Okay. Changing the spin quantum number. So we'll see later that a triplet state, you know, if you have electrons, they can be up or down, right? And if they're paired like this, they are energetically favorable. If you have two spins that are up, they are repulsive. We'll get to that in the next class, okay? So for the moment, we just say either they have a spin flip or they can involve some symmetry considerations. Or they can concern, the number of excited electrons at a given time. Oops, time. So you cannot have, you know, it's unlikely that you have at the same time 2 or 3 excited electrons in the same molecule. That would be quite unstable. Okay. Okay, so let's list some of these energies. So we start from the lowest. So N2 pi star, N2 sigma star, pi to pi star, sigma to pi star, and sigma to sigma star. Okay, so only two of those are allowed. This one and the pi star. The rest are forbidden. Okay, so I'm going to put a little asterisk here. So forbidden, does that really mean they never happen? No. So it's forbidden, but often still observed, but weaker than, switch back to green, allowed ones. Okay. And another little note. This is the most commonly observed forbidden transition. Okay. So where do these transitions usually happen? So in alkanes, right? So in an alkane, you only have sigma bonds. So you only have sigma orbitals, right? In carbonyl compounds, we'll get back to the carbonyls. In alkenes, alkynes, so double bonds, triple bond, azo compounds, and also in carbonyl. This one in oxygen, nitrogen, sulfur, and in halogens. And this one also in carbonyls. Okay. Okay. So transitions between molecular orbitals are quantized, right? So you have exact energy levels. Okay. But the peaks that we see, that we observe are broad. So they have a range of energies. Why? Okay. So why don't we see infinitely sharp peaks in the UV-vis absorption spectrum? Okay, let's try to draw that. So here we have energy. Okay, so we have the ground state. And we have the excited state, right? Electronic excited state. Okay, so if we would just look at this transition, it would be super quantized, super exact, only one energy. But in reality, we have additional smaller levels, and they are somewhere here. And those are vibrational levels, and they are very close to the electronic states, right? So I have these things, oops. And so we can call them V1, V2, V3, V4. V1, V2, V3, V4. So those are vibrational levels. So we saw in the previous class that electronic transitions are on the order of 1 electron volt, and vibrational energies are on the order of 0.1 electron volt. And then in between those levels, cannot really see them, right? So I'm going to do a little zoom. Oops. Didn't work out. So here you would have even more levels. Cannot barely not see them. Those would be rotational levels, right? On the order of 0.01 electron volts. Okay, so now if you are looking in the real experiment, what are we really exciting? We are not only exciting from the electronic ground state, you know, we're not only doing this transition, right? We are also exciting, for example, from this vibrational level to this vibrational level, or from here to here, or from the ground state to some vibrational level, right? So there are energies that are closely related, but they are not exactly identical, right? So if we look at the absorption spectrum, absorption and wavelength, then, you know, in theory, you would just have one line, right? So that's if you would only have E0 to E1. It would be an infinitely thin peak, right? Because there's only one exact energy. But because we have all these vibrational and rotational levels, what you will measure is something like this, right? So in the reality, you have this, including, it's called superimposed vibrational and rotational levels, right? So the width of the peak, sorry, this should be at the same position. Okay, right? So the peak is not infinitely narrow like the theory says, but it has this smaller levels that are close, which are also accessible, which makes the peak broader. Okay. So, very important, Lambert-Beer law. Okay. There we go. So how is a photon absorbed practically? So the photon has to meet the molecule, right? And the molecule has to absorb the photon. So in the previous class, we said, okay, the energy has to match, the transition has to be allowed. But if the photon doesn't actually hit the molecule, then you're not going to absorb anything, right? So if we think about that, so the absorption should depend on the number of molecules in the solution. What is that? It's the concentration. Let's call it C. And the distance, or as they call it in UV, the path length the light travels through. So through the solution, right? L, we'll call it L. Okay, so, and in addition, the energy, right? Energy has to match the transition. So this was delta E is h nu, plus it should be allowed. Okay, this was from the previous class. Okay, so let's now call the absorption coefficient eta is the probability that the molecule will absorb. So for example, if delta E is not h nu, then epsilon will be 0, right? If the energy of the photon doesn't match the transition, your absorption coefficient is 0. So it's a molecular property, right? So now, what is this Lambert-Beer law? It says that the intensity of the transmitted light is the intensity of the incident light. Right, so this is transmitted light. And this is incident light times 10 to the power minus epsilon times C times L. Right? So epsilon is the absorption coefficient, C is concentration, and L is the path length. Is this still working? What's going on? Wow. Low battery. Great. Do you hear me, or okay? Okay, I'll try to speak a bit louder. So the absorption coefficient, this depends on the molecule. And the other two, this depends on the experiment. Right? I can, I'm doing the experiment. I take my molecule, I weigh it, I make a solution, so I can control the concentration normally. The path length, what does it mean? You have a cuvette, which is a certain length. Usually it's 1 centimeter. You also have 1 millimeter, 100 micrometers, or 10 centimeters. But typically it's 1 centimeter. Okay, so I can control this. So the more typical form of writing this equation is you take the 10 log of this, right? So the absorbance A is the logarithm of I incident over I transmitted is E times C times L. And again, we have to look at the units, right? So concentration is in molar. Path length is in centimeters. So the molar coefficient, because this is absorbance is dimensionless, right? So this has to be per molar per centimeter. Okay. So for example, this pi to pi star, the absorption coefficient is about 10,000 per molar per centimeter for an allowed transition. Whereas for example, n to pi star, so the most common forbidden transition, it's 10 to 100 per molar per centimeter. Okay, so it's forbidden, but because of this vibronic and rotational levels, it can still be observed, but very weakly. Okay, so, sorry. So what can we determine? And this will actually be most of the part of the, I hope you all took the TD spectroscopy. If you don't have it after the class, you come and pick one here. You have to do exercise 1 to 5. Okay? For your, before the TD of Professor Samori. I don't know exactly when it is, but it's probably this week. Right? And so there will be exercises, and they have different types. So one would be, you know the concentration and the path length, and you have to determine the absorption coefficient, right? So that's simple because that's A over C times L. Okay. For example, another one is, you know the absorption coefficient and L. Determine the concentration. Again, simple because C is A over E times L. And the third one is, move this a bit to the left, is you can follow a chemical reaction. So for example, you have, and we'll see that later, you have a molecule which has an absorption, okay? let's say like this. It has a certain lambda max, and this molecule, for example, breaks down, it reacts, and therefore its absorption decreases, and the product has probably a different absorption, and this one will increase. So if we extract, so we're going to extract the absorbance at these maxima, right? L lambda 1 and 2. Then this line would be something, no, sorry, this autocorrect thing sometimes is a bit weird. Okay. Okay, we'll see that in kinetics, okay, but this one will decrease and this one will increase. So this will be the absorbance at lambda 2, and this will be the absorbance at lambda 1, and this is versus time, right? So if I have, this looks like second order kinetics, I will have some kind of exponential decay in my signal. Okay. So when we look at the experiments, what comes out of the UV vis spectrometer? Okay. Been drawing a couple already. So it's the absorbance on this axis. And it will be typically 0, 1, 2, 3 maybe. And here I will have wavelengths, maybe 300, 500, 700 in nanometers, right? Absorbance doesn't have units, dimensionless. And we'll have some kind of curve, right, with lambda max. Okay. So also on the y-axis can also be the absorption coefficient, because absorbance depends on concentration and path length. So if I take a different cuvette, then my absorbance will go up and down. If you plot the absorption coefficient, it's independent of the size of your cuvette and of the concentration. So it's a more logical thing to plot, but still most people plot in scientific papers, you will plot absorbance. So what does it mean if I have absorbance 2? What does that mean in the experiment? Let's go back to the equation. Absorbance 2 means what? It means that the log of the incident and the transmitted light is 2. But what does it mean? It's 10 to the power something. It means that the transmitted light is 100 times lower than the incident light. It means you shine light on the cuvette and only 1% comes out. 99% is absorbed, right? So absorbance 2 means 99% is absorbed. Absorbance 3 means 99.9% of the light is absorbed, which basically means there's no more light coming through the cuvette, right? So often you have to, you don't care about this now, but in experiments, if you want things to be quantitative, You want the absorbance to be less than 1. You know, otherwise, because your detector has to actually catch some light. Okay, let's look at some other aspects. Influence of the solvent. So in UV vis, you're not working in a vacuum, right? You're typically putting your molecule into a solvent. So you have to consider the solvent cutoff. What is that? So it's the wavelength below which all light is absorbed by the solvent. Okay, so for example, EG means for example, acetonitrile, some solvents, N-hexane, or trimethyl phosphate. The cutoff will be 190, 201, or 210 nanometers. So if you are trying to measure an absorbance of a molecule that is at 205 nanometers and you put it in trimethyl phosphate, you can never measure it because the solvent, you know, your solvent always, I mean, almost always has a much higher concentration than your molecule, right? So if your solvent absorbs your light, then you cannot measure anything. Okay, so that's the solvent cutoff. What also is influenced by the solvent? Influences the what's called fine band structures. So what is that? So let's draw a spectrum. Okay, 220, 240, 260, 280, 300. And here I have absorbance. I'm going to attempt to do this correctly. Right, so also for molecules, when you go to this lower than 220, your absorbance will always go up. Now, so typically you don't measure below 200 nanometers. This is the spectrum for phenol in a solvent called isooctane. Okay, so now if I take the same molecule, but I put it in ethanol, I will get something like this. Okay, let's make it dashed. So in ethanol is a polar solvent, right? And it can do hydrogen bonding. So it forms, so if you have a solvent that can form a complex, it can do hydrogen bonding with your molecule, you will have more vibrational possibilities. So your peaks become even broader, right? If I have isooctane, it's apolar. So I have fewer vibronic structures possible. So fewer vibronic structure, fewer rotational structures means sharper peaks. Okay. But in general, so I didn't draw it very good because the area under the curve should stay constant, irrespective of the solvent. So some solvents will be sharper, some solvents will be broader, but the area under the curve, because that represents how many photons are absorbed in total, and that will not depend on this shape of the curve. Okay. Oops. There we go. So 3. So the solvent polarity and hydrogen bonding capacity, they shift transitions. Okay, not only do they change the broadness, but also they can shift the position. So for example, if we look at acetone, and we put acetone in different solvents, and we look at the lambda max in nanometer, okay, then in water, in methanol, ethanol, chloroform, and hexane, right? It will be 264, 270, 272, 277, 279. Okay. So as we'll see later, there's a red shift, like the absorption maximum shifts to longer wavelengths. Okay. I'll come back to that. Sorry, I have to go a bit fast because I lost 20 minutes at the beginning. Sorry about that. So we'll talk about the energies and intensities of absorption peaks. Okay. So for alkanes, we are mostly looking at sigma to sigma star. Very short wavelength. So typically not observable. Oops, doesn't fit. Right, so this is just a practical limitation of the machine, right? This absorption will maybe be at like 180 nanometers, but typically the machine cannot observe 180, right? So if we just look at the orbitals, right? So if we have a carbon-carbon bond, the ground state and the excited state, right? So if we look at the orbitals, they're going to look something like that, right? And they will have some kind of energy levels. So this is sigma, sigma star. We can have a transition here, right? Sigma to sigma star. And originally we have 2 electrons in that energy level, right? And we can have a transition from, okay, it's a bit difficult to draw, but you can have this transition from these two electrons here, and they will hop to that orbital. Okay. So for amines, alcohols, or sulfur compounds, we're looking at N to sigma star transitions, typically 175 to 220 nanometers. But again, this is typically below the solvent cutoff. So it means you practically cannot observe them because the solvent will absorb in the same region, usually. Okay, then we go to more interesting things like carbonyl compounds. Okay, wait. I have to. Sorry. Okay, so carbonyl compounds. So we're going to look at, okay, let's draw the carbonyl first, okay? So carbonyl, like this, right? And that will have N to pi star 280 to 290 nanometers, absorption 15, pi to pi star around 188 nanometers with a higher absorption, okay? Okay, let's draw the levels. Okay, so that's always a bit of a difficulty. Okay. So we have the sp2 of carbon. In each orbital, we have one electron. We have the pz orbital of carbon with one electron. And then we have a little bit lower, we have the py of oxygen, pz of oxygen. And then even a bit lower here, we have sp of oxygen. Okay, so we have 3 electrons here and 3 electrons here. Okay, so now let's look at all the possibilities. So we can have an orbital here. This one will be from the non-bonding. Line it. This one will be a bit lower. This one will be here. Here. Okay, something like that. Okay. Okay. Almost there. Okay. So some colors. So this would be sigma, non-bonding, pi, non-bonding, pi star, sigma star. Then we fill the electrons. So you have 2 here, 2 here, 2 here, and the non-bonding has the last 2. Okay. So again, this is the HOMO, and this is the LUMO. So those are the transitions we're going to see, right? So this is carbon and oxygen. Okay. That's for carbonyl compounds. So you can look at the atomic orbitals, make the molecular orbitals, look at the levels, and then this will make sense for the transitions. Okay, so some last things we need to look at. Conjugated compounds. I'm going too fast, too slow, too fast. Sorry. Fast? Sorry. I have a couple pages to get through, so. Okay, but the rest is simple, okay? So if we look at conjugated compounds, for example, okay, you know conjugation, of course. So what does the absorbance do when I get compounds that are conjugated? Okay. So I'm going to plot the absorption coefficient in per molar per second. And I'm going to plot the wavelength in nanometers. Okay, so I have like 200, 300, 400. So depending on the length, so let's look at the shortest one. I will have something like this. N is 2, right? This N. Then there are two things that happen. The first thing is that when I go to more conjugated compounds, I get a shift, right? I get a shift, but I also get a higher absorption coefficient. Right? So if I go to 4, okay, it's not very accurate actually, sorry. Should be a little bit more somewhere here. Okay, so the energy, the delta E of this pi to pi transition, pi star, sorry, decreases with increasing N. And the absorption coefficient increases with increasing N. Okay. This is also the case for aromatic ring systems. So also for aromatic ring systems. For example, if we look at benzene, This is benzene. Naphthalene. Anthracene. And naphthacene. So if we look at lambda max and the absorption coefficient, so we see that the wavelength will increase to 86, 375, 477. And also the absorption coefficient 60. So you see that there's this huge difference between benzene and naphthacene in terms of the absorption coefficient. So now we're getting to an interesting point, because we go to something called chromophores. So the definition, so it's the part of a molecule in which the electronic transition for a given spectral band is localized. So often it contains pi conjugated parts, electrons, giving compounds that are visibly colored, also known as pigments. So, okay, chromophores are basically conjugated molecules that have absorbances in the visible, so they will have a real color. So it's not, benzene is a transparent liquid, doesn't have any color, but naphthacene will have color. Okay, so just two little examples. Oops. I'm not drawing this very well. Okay, so that's 5-membered. Okay, this one is called indigo. So will be blue. And another simple one will be OH. This one is called alizarin, and this one will be red. Okay, we're getting to the last points. So something about how to call things. So horrible word, but it's the same in French, right? Nomenclature. So when we talk about UV-vis spectra, things can, under the influence of certain things, can shift Okay, wait. I'm going to draw this a little bit lower. Okay, so absorbance, lambda. I have some kind of spectrum. And now depending on what happens, so I can have a shift of these peaks. So the most well-known ones, so this one is called bathochromic shift. So it shifts to the right, and this one is called red shift. In other cases, you can have, it's called hypsochromic shift or blue shift. So that means your spectrum moves to the left to shorter wavelengths, more to the blue, right? In the rainbow, you have blue here, and you have red here, right? So if something shifts to the right, you call it red shift, and if something shifts to the left, you call it blue shift. Then there are situations where it shifts up. So this you call hyperchromic shift. And when it shifts down, you call it hypochromic shift. Okay, so that's cool. So when you know, how does this shift? What's the cause? Okay. So one reason, there are many, but I'm just going to highlight a couple. It's called solvatochromism. So that means chromism means moving the wavelength, and solvato is from solvent. So if you have positive solvatochromism, you have a red shift. Usually that's in a more polar solvent, right? If we have negative solvatochromism, we have a blue shift. So we have decreasing polarity. Okay. This will be in your TD, halochromism. That's a very, very fancy name to say pH indicator. So you probably did some pH titration in TP in the first year, I hope. So that's a color change due to protonation. Right, you protonate the dye, it usually shifts its absorption. And the range depends on, on the pKa value. Some have multiple, right? So the pKa determines, you know, if the pH is at the pKa, you have 50% protonation, right? Okay. Another reason can be self-assembly. I like this one because we work on that. So in self-assembly, you have non-covalent interactions that lead to larger structures. Okay, so let's say I have a molecule. And it's in a monomeric state, right? And now the molecule can self-assemble, right? It can do it in different ways. It can stack like this, straight. There's, for example, hydrogen bonding between those. Or it can do something like a little ladder, like this. Okay. So this is called an H aggregate. And this is called a J aggregate. And okay, it's too much for this class, but basically the dipole moments of these molecules, they influence each other. And therefore you get, in this case, a blue shift. And in this case, you get a red shift. Okay. There are many, many other reasons. So they all end in chromism. So there's, for example, thermochromism, photochromism. So thermo means with temperature, photo means you shine light on a molecule, it changes color, which is cool. You can have electrochromism, you can have piezochromism, hydrochromism, chronochromism, that means with time. Sorptiochromism, that means if a molecule absorbs on a surface, it can change color. Mechanochromism, that means you exert mechanical force on the molecule, it changes color. So there are many, many, many. Okay, so we're getting to the end. So I'm just going to show one last thing, which is how that's okay. Let me share. I'm just going to switch. Okay. So that's the inside of a UV-Vis spectrometer. I'll put this on Moodle so you can just copy it. So basically you have different kinds of lamps, either a deuterium lamp or a tungsten lamp. So why have two different lamps? Because they have different emission wavelengths, right? So different lamps have different colors. So you need to span the whole range from 200 to 900, you need different lamps. Then you filter basically one wavelength. So you make the filter and the monochromator together make light of one specific wavelength. So maybe 350 nanometers. And then a beam splitter does what it says, right? It splits the beam of light into two parts. One goes through your sample, and one goes through a reference. So this reference is the same cuvette of the same material with the same solvent. So you're subtracting basically the background of the solvent and of the cuvette from that. And then you take the difference between those two, and that gives you your spectrum, right? Which gives you absorbance versus wavelength. Okay. This is just for you to know if you need it. So depending on the classes of molecules, alcohols, you can look up what's the most typical absorbances and what is their absorption coefficients, and some lambda max of conjugated things. We're almost done, almost. I just want to show you one little cool thing. Right, so in this, so this is from our research. And so we have this molecule, this is a chromophore, right? This is a perylene diimide, it's conjugated, and it has this pink color, right? So now we're going to change, so this one actually changes color due to a redox reaction. So if we add a reductant, sodium dithianide, we go to this blue state, which is a radical anion, or to a dianion. So I'm going to play this movie. So just look at the movie. We're going to add the reductant, dithianide, it goes to purple, right? So we have this deep purple color. It's open to air, so oxygen is coming in. Oxygen is an oxidant, right? It oxidizes the molecule to the radical anion, which is blue. And then it oxidizes further back to the neutral state, which is again pink. So this molecule changes color with redox state, which is nice. And actually, if you look, so this is the UV vis spectrum. Why do we have here now not absorbance? Sorry to confuse you. Here we put optical density, because remember in the first class we said light can be absorbed, but it can also be scattered or it can be reflected. So optical density takes those things into account, right? So in our case, you see that we start at this black spectrum, and then when the molecule self-assembles into bigger structures, you get a red shift, right? So we get J aggregates, but we also get this new transition here, and we get the baseline goes up. This means there is light that is scattered. So I cannot call this absorbance, because it's not only absorbance, it's absorbance and scattering. And that's why I call it optical density. And so in this case, we track this frequency, 528, versus time. And that tells us something about the kinetics of this assembly process. Okay. And under certain conditions, this color changes spontaneously, repetitively. So it can oscillate in color, which is cool to look at. And if you want to read everything, you can go to this paper. Any questions? Okay, thank you. Have a nice day.